Hi, welcome to these Mastery Check 12.1 notes. They're to get you ready for the first Mastery Check in the electric potential unit. Let's talk about gravitational fields, and then we're going to talk about electric fields. A bit of a comparison here. So just to change things up, I went with the moon instead of the Earth. If we're going to talk about the gravitational field close to the moon, here I can draw the moon as if it's just a flat thing because we're zoomed up close to the surface, and we would have a gravitational field G, and instead of 9.8 it would be about 1.6 newtons per kilogram. And the way we could diagram that is a bunch of arrows that are going downwards. So that's the direction of the field on the moon. So how about if we were going to try, and this would be a very uniform field in the sense that whether I'm here or here or here, it's still 1.6 newtons per kilogram. If I got really far away from the moon, it would get a little bit less. Now let's think about electric fields. The way to make a uniform electric field is by having charged plates or a bunch of charges lined up in a line like a plate. So if I want to have the direction of the electric field the same in this case. Remember, electric charges are going to go away from positive, or electric field will go away from the positive and towards the negative. If you forget which direction it would be, is if you place a tiny little positive charge in there, and you think which way would it experience a force. So in this case it's going to go away from the like charge and towards the opposite. So this would go this way. So the force on a positive charge is the same direction as the field. If it was a negative charge, of course, then it would be going the opposite way. So that's the way to think of it. Okay, so there's our example between the gravitational on the moon and electric field between two charge plates. So we can do a couple little formulas here. How can we figure out? I'll do for the gravitational, and then let's see if you can do the electric equivalent. So the gravitational field in this case would be G is equal to, well, we have that 1.6 newtons per kilogram, but how could we figure out a formula for the field strength? Well, I'll give you a hint. Let's go here first. Force of gravity is equal to the mass multiplied by the gravitational field strength. Mass is in kilograms and field strength is in newtons per kilogram. So if I rearrange this for G, I would get Fg over m. Okay, so what I'd like you to do now is try to do the electric field example on the other side. So if I put over here field and force. Can you try those right now? So hit pause, see if you can put in the equivalents. Oh, by the way, this is the symbol I like for electric field. I like to do this kind of an E, because if I use capital E, it looks like energy. So I'm going to start you off with that. Okay, give it a shot. Okay, hopefully you've given that a try on your own. So if I went into the same order like this, the formula for force, now it's not gravitational force, it's electric or electrostatic force. I just usually say electric force. Now it's not going to be a mass which is going to have an influence, it's a charge, and the charge we use the letter Q and then multiplied by the electric field like this. Quite often we end up seeing this formula with the E and the Q the other way around. So you can write it either of those ways. So if we solve for electric field, we're going to get Fe over Q. Okay, and by the way, then the units are going to be newtons per, not kilogram in this case, but newtons per coulomb, which is the amount of charge coulomb. All right, let's try the next section here, potential energy. So I'll do the same thing. I'll do potential energy for gravitational fields. It was, Eg was equal to mgh, where h is the height. So what would be could you try the electric version now? So hit pause, see if you can do the electric version. So instead of Eg, in this case, we'll do Ee. So it is a bit of a problem because this was also what we used for elastic potential energy. But I think we'll be smart enough to realize that that small e could mean two different things. Instead of mass, the equivalent would be charge, so Q there. Instead of the gravitational field, it'll be electric field, E. And then we can still use the H But we have to think about what this h means. So back over here, if we took an object here that had a mass and took it from here and brought it up here, this would be the height that we moved it. If we took that same one and put it up an inclined plane maybe and put it over here, again, we would be measuring this height. So it's actually the distance against the field, if that makes sense. So because the gravitational field is going downwards, this h height, and we instinctively understand that height means that upwards, which is against the field. So if we moved a charge here, again, this height here, we usually don't use height, but we'll probably just say some distance here. We can use a d. This distance against the field. So again, if we took this positive charge and we started it over here, right, and we moved it over here, really we would be just interested in this as our distance that we moved it, okay, not the diagonal line. And if we took it from here and we moved it over here, there's no change in potential energy, okay? This is where it's lowest in potential energy. This is where it's highest in potential energy. And just like we are moving something, move a rock up the hill and there's more potential energy because it's higher, here, again, you can think, okay, I'm moving this charge against the field. So it's like moving it uphill. And so it's moving from a lower place to a higher place. Okay, now potential or potential difference, and I'm going to write this out. Another way to write this, we can say this is potential equals potential energy per mass. Okay, so this will make sense then. We'll say this is going to be equal to Eg over m. Well, could we write that out? Then that would be equal to, well, actually, we'll just leave it like this. So it'd be the potential energy divided by the amount of mass. Now, we don't actually have a letter, so I'm just going to say gravitational potential is going to be equal to Eg over m. And the units for this, energy is measured in joules, and the mass is measured in kilograms. Okay, so if I say here, I'll clean up my diagram a little bit. If I get rid of all this stuff here, if I put a mass here, I can calculate how much potential energy it has. Well, I guess it would be 0 right there. So Eg would be equal to 0. If I went up here and put it up there, I could find out how much potential energy it has. It would be mgh. If it was, say, 2 kilograms, right, and I moved it up 1 meter, it would have some amount. The potential energy per mass doesn't need to know what mass I'm placing there. I'm going to say, how much energy does it have per kilogram? So in this case, let's say this location in space, that location in space has 10 joules per kilogram. If I moved a 1 kilogram mass there, it would have a potential energy of 10 joules. In other words, it would take 10 joules to take something from 0, 10 joules for every kilogram up that hill. Okay, hopefully that helps. Can you try to do the same thing now for electric? So again, this line will be exactly the same, so that can go all the way across. But here, instead of gravitational potential, it's going to be electric potential. So see if you can solve that. Okay, so electric potential equals EE over, now not mass, but charge. And the units will be joules per coulomb. Okay, now we do have a letter for electric potential, and we do have a special unit which is equivalent to joules per coulomb. So we can also use, instead of electric potential, we can use V. And is equal to EE over Q, and another, besides joules per coulomb, we can use volts. So it's a bit of a crazy one in that the letter we use is V, and then the units is volts. And in order to make sure I don't get confused between velocity, here, don't get so crazy, I like to use uppercase V for volts. Okay, the last one they talk about is potential difference. So potential difference would be the difference between one location and another location. So let's say if this location over here had a potential of 5 joules per kilogram, I could say between these 2 points, say between A and B, that would have a potential difference of 10 minus 5. So potential difference, here I'll put in, over here I'll say, I'll just do the electric version here. So potential difference the way we could write this would be delta V, right? And we could call this V2 minus V1, or we could also say the change in electric potential energy divided by the charge. So we can think of it as either way. Here's a question that says, how does potential energy differ from electric potential? Well, potential energy, this one here, is Eg, and it's equal to mgh. The electric potential here is V is equal to, oh, sorry, it's electric. I went back to gravitational. EE is equal to the charge multiplied by the field by the height within that field. The electric potential is EE per charge, and this one, I guess the big difference between these two, this is the potential energy of a given charge, and this one over here is does not require a charge. It's the potential energy per coulomb. Okay, this one here is similar to height. Okay, I hope that's okay. So what you'll be required to know for the mastery check is this is one of the few times that I actually want you to know I want you to know those formulas. Okay, I want you to know this. Okay, and I want you to know this. Okay. How to solve for those. I'll give you some numbers and you can solve for those, and I want you to be able to answer this question too as well. Okay, so hopefully that will be helpful, and if you have any questions, I'll see you in class.